All right, let's look at our last set of nitrogen nucleophile-based reactions. This reaction is called the wolff-kishner reduction, and it takes a ketone or aldehyde and removes the carbonyl, very much like the Clemmensen reduction. Interestingly to note, the wolff-kishner reduction is a basic reaction. It requires mild acid to put the hydrazone on in the first place, but then the second step is strongly basic conditions. And so we will remove our carbonyl completely, producing nitrogen and water over the course of the two reactions. This is compared with the Clemmensen reduction again, which uses a strong acid, HCl, along with the zinc and the mercury. So this one is better for base immune molecules, rather. So if your molecule can handle the base, then the wolff-kishner is better. If it can handle acid, you'll want to go with the Clemmensen. And of course, you'll have your option of either one, technically, if you have no sensitive functional groups. So in the first step, we're going to convert our carbonyl into a hydrazone. And then from there, in step 1 and then step 2, we're going to eliminate it. And so we're going to look at the mechanism of this reduction and how we get the nitrogen to leave. All right, and this is conducted in the presence of aqueous strong base, so sodium hydroxide, potassium hydroxide, pretty commonly used here, along with some heat because this is an elimination. All right, let's take a look at it. So assuming we have the hydrogen already, because we've looked at that formation with the imine, that's essentially an imine, except we have a nitrogen instead of a carbon on our double bonded nitrogen. So let's take a look here. So in basic conditions, we're going to go ahead and have our hydroxide come along, and it's going to go ahead and cause a bit of resonance to happen as it abstracts a proton. And in doing so, we end up with a negative charge on our carbon, which is immediately going to say, I am not happy. I'm going to go ahead and grab a proton, which it shall do. It will find our dear friend water and grab that off, remaking our base. So we're going to end up, this one's not really an equilibrium step. It kind of is fairly irreversible because carbanions are not easily formed. So we have our next hydrogen there, which will go through the same process. Here's our OH minus. I'm going to go ahead and grab the proton. And again, we're going to now form a triple bond between those nitrogens. And we're going to form another carbanion. This one is an absolutely irreversible step because this one produces nitrogen. So we're going to lose nitrogen gas. That bubbles away, it's gone. It's out of the picture. We're left with this carbanion, which is simply going to very rapidly go ahead and grab a proton off of a water molecule. Reforming our base. So this is a base catalyzed process. And then that's going to go ahead and irreversibly form our alkane, it could be, or whatever. It's just completely gotten rid of our double bonded O. So first step, we're going to deprotonate, causing a carbanion to form, and immediately protonate that. Once that happens, we have another deprotonation step. We remove the second hydrogen on our hydrazone. It's going to now eliminate the nitrogen gas. That's N2. So it bubbles away, it's gone. We're left with this carbanion, which immediately protonates itself because it's terribly unstable. and we are left with our product, which has nothing. So again, this is useful. You can use this with your Friedel-Crafts acylation reaction. If you have something acid sensitive and you need to use basic conditions instead, you'll want to use the Wolff-Kishner reduction to get rid of your ketone or aldehyde. Again, otherwise, it can be useful if you need something removed, but it's kind of a last thing to do, right? Once we eliminate it, it's gone. And now we have a non-functional molecule, at least in that same area. And so that's our last one. So the Wolff-Kishner reduction, in summary, you treat it with hydrazine and mild acid. In the first step, you form that hydrazone. In the second step, you add strong base, aqueous, with heat, and you will eliminate your carbonyl. So you'll end up with just an alkane, or a methylene group, rather, we can say, the CH2, where your carbonyl used to be. And that's it for nitrogen nucleophiles. So in our next one, we'll look at sulfur as our next nucleophile.